Let's kick it off here. Well, first of all, thanks again for anybody that's joining our session here today. It's really appreciated. My name is Lenny. I'm with Flow Software. And what I'm going to do today is I'm going to talk to you about a little bit of aggregation methods and the capabilities that the Flow Software platform has when we talk about cleaning up data and performing aggregation methods on data. Now, this is one of our first Flow Tech series that we've been launched. So every 6 weeks or so, we'll be having a little bit of a tech session. It's an hour session where I take a topic within the Flow system and I talk a little bit technical around that topic and just show you guys a little bit of what the platform is capable of. And I thought a good way to kick this off is to understand what Flow does with data and how does Flow clean data, add context to data. And that's why I thought talking about the little bit of aggregation methods that we have in Flow. You'll notice that we do it in a series, so you probably have some invites for the next two parts in our series, but I'll discuss that at the end of the call, what the next topic is going to be in about 6 months or 6 weeks time. Great. Now, before we go into the aggregation methods that Flow can perform on data, the first thing I just want to talk a little bit about is data handling and how does Flow get the data from our sources to perform these aggregation methods on. Now, on a typical kind of plant environment, we have our PLC devices that physically go and control our plant. So all the controllers programmed into those PLCs. There might be some status bits of process variables that we need to analyze. And there's also some state engines potentially for filling lines and machinery. But literally the PLC is what controls these different pieces of machines. Now, what we normally do with PLCs is we connect it to some kind of OPC server, right? So the OPC server will do the little bit of the language translation for us. So it will connect to those PLCs, whatever brand or flavor those PLCs are, and it will convert all the tags and all the information that we can get to it into a standard like the OPC DA or OPC UA standard so that we can go and connect to that data. And normally on top of these OPC servers, we would then go and employ a historian. Now the historian will go and store all of this high resolution data as it changes in the PLC controllers. It will store that into a time series database that we can then use either as technicians or engineers to look at trends and to do our technical analysis on the data, potentially for fault finding on that. And obviously we can store all of the bits and all of the data from all our different PLCs into this one central historian. Now, where Flow fits in is Flow fits on top of this historical data. So that's a very important concept to understand, is that because Flow performed these aggregation methods on top of historical data to clean it and to add context to it, Flow needs historical data. And one of the probably the most common data sources, but not the only one, is plant historians that we connect to. So the Flow information platform will then collect the data from the historian. It will apply these different aggregation techniques on it. We can then use these different aggregated measures to calculations and KPI calculations, and then also go and add context to our data. We can also then use that context or those pre-aggregated data to send that to BI tools, to other systems that might require it, like ERPs, etc. So I just want to kind of to paint the picture a little bit on how we will handle data coming from a particular plant environment. But as I mentioned, historians is not really the only source of data that we can get into Flow. And I think that's one of the strong points, is that we can have multiple data sources connected to the platform at once. So I'm just going to quickly, very highly go through a little bit of a pseudo architecture of the Flow information platform. And the first thing that we do with the platform is exactly that. We collect data. So we connect to all of these different data sources that we have on our plant environment. Now, as per the previous example, it could be historians, but it could have also been a transactional SQL database that could potentially host MES data or batch data. It could have been a cloud solution. Maybe you're using a cloud solution for all your energy meters, etc., and you want to get that data into the platform. It could have been an IoT platform. And very, very critical, there's still data that we manually collect from our plant information. Could be a flow transmitter or a water mains pipe that you don't have automated as yet. That value does not go into your historian, but you still want to use that information inside of your calculations and KPIs. So it's very critical for you to also be able to add manual data into the platform. The flow engine will then go and perform these different types of aggregation methods that we can apply to the data, as well as all our roll-ups, as well as all our custom calculations and KPIs that we can go and configure. So the flow engine is really the heart that performs all of this hard work to clean the data for us. And then, obviously, with that clean data and those KPIs and measures, we can then go and present them in a nice dashboarding capability or reporting view. So the Flow Information Platform has the capability to create these dashboards, to visualize all our KPIs, and we also have a little bit of a mobile app that we can send these reports and dashboarding out. It's a little bit of a notification and collaboration framework between your colleagues on the data and on the KPIs that you've configured. Now, as I mentioned, we are definitely not a closed system, and there might be other systems that would like to have this repository of clean data, and we have a mechanism to integrate the data out of Flow into these systems. So we can push data to an ERP solution, to another SQL database that might require, to BI tools. We can even push that KPI calculation back potentially to a SCADA environment by using the MQTT protocol, so that the operator on the plant has a view of his hourly or daily KPIs and how far is he tracking against that. And we can even send that to another Flow system if we have a multi-site scenario and potentially head office or the enterprise level would like to see and compare and benchmark different sites with one another. We can go and push that data up to what we call a tier 2 flow. So I just quickly wanted to kind of paint the picture of the different components of Flow, how we can connect to these different data sources that we might encounter in our production facility. And obviously, we will then perform these different aggregation methods on top of it. So one thing to realize is that the first piece of context, we've been speaking about that a lot, is that Flow add context to data. Now, the first piece of context of data that Flow will apply to data that's coming from these different sources is the context of time. Now, what do I mean with that? It could be as simple as an hour, a day, a week, a month, or a shift. So we can perform these aggregation methods based on these different time frames that we can go and configure inside of our Flow Information Platform. So what I've got on the screen there is an example of a boiler temperature. So that is the raw temperature as it's been historized inside of my historian. So this is the raw time series data that we will now collect and perform an aggregation method on. So if I tell Flow, you know what, I would love to know what is, as an example, the average of the temperature for the hour, what Flow will do is it will go and create what we call these hour time buckets. So it will go and query our historian for a particular hour, and that Flow engine will do this in the background automatically, and it will get all that raw data points. And for that particular hour, it will then go and perform whatever aggregation method we apply to it. So in this case, probably not the best example for temperature, but we'll discuss that a little bit later when I go through the examples. But in this case, just a plain simple average on the data that we've got there. So the Flow engine will go through all of these hourly buckets of the data. It will perform the average aggregation, and you'll notice that it will do that until it's up to time, and then for the next hour it will perform the aggregation again. Now what we store inside of the Flow database is just the result of that cleaned data. So we do not replicate all the raw data that sits in our historian. We only store the result of the aggregated data inside of the Flow ODS, and that is then the value that will be presented either through our dashboarding or reporting solution, or that would be the value that we can then send or integrate to other systems like ERPs and other databases. Now, it's also very important to understand what the data looks like when you apply different aggregation techniques onto it. So in this case, it was a simple process variable. of temperature. As the temperature changes, we log it and we perform an average aggregation on it. But what if it's been a totalizer? So this is a totalizer of a piece of equipment that totalizes either by the instrument itself, or there's a function in the PLC that does the totalizing for us. In this case, I cannot perform an average aggregation. An average aggregation is not going to give me the answer, because what I would like to know for totalized process variables is how much did I produce in the individual hour time buckets. So again, Flow will create the hourly time buckets for us. The engine will run through these raw values, but now instead of doing an average aggregation, we will go and do what we call a counter aggregation on top of it. So because we want to know what was the first value in the hour, the last value in the hour, subtract the two from one another to get the actual total for that hour production. And again, we will run through all of these time buckets in the historian, and we will query the raw data and perform this counter aggregation method. Now, very importantly, and we'll discuss it a little bit later, we also need to know, obviously, when there was a rollover that occurred in that totalizer value, so when it resets to 0, and we need to be able to cater for that when we do these different aggregation techniques. So again, that one result will be stored inside of the Flow ODS database. That's been then presented either on the dashboard or being pushed out to another system. Now, what is the different aggregation methods that we can configure in Flow? So when we create a KPI or a measure inside of our Flow system, and it could be either queried from a SQL database or from an historian, doesn't matter, we can go and, by means of a little drop box or drop down item here, select a whole bunch of different aggregation methods. And I'll go through all of these aggregation methods here in a moment to explain exactly what each and every one of these aggregations do. And if these things don't give you the answer that you require, you can even go and create what we call a custom one, so that you can go and customly create whatever aggregation you want to deploy onto your raw data. But before we go through all of these methods, let's just look a little bit about the data that we're going to apply these methods from. So I've created a little sample data set. It's from 6 o'clock in the morning to 7 o'clock. So I'm looking at an hour worth of data. And these are all the different points that I've got historized inside of in my historian. Now you'll notice that out of these 14 data points that I've got on the screen, there's one data point that's actually before 6 a.m. in the morning. So at 55 past 5, so 5 minutes to 6, there was a data point. And then again at 5 minutes past 7, but it's outside of my 6 to 7 window that I'm querying the historian for. If I plot this on a screen, it might look like that. So there's my hour time frame, and in that hour time frame, I've got 12 records in the time frame. Now, you'll notice that obviously that point sits outside of my time frame, the first point, and I also have that last point that sits outside of it. Now, one concept that we have in Flow, and it's very important to understand because a lot of the aggregation methods will use that, and that's the concept of what we call a boundary value. Now, it's very important to also understand is that Flow does not do any interpolation of the data points. So what does that mean? So that means when I take these 2 points, the first point that I've got there that's outside of my 6 o'clock window, and the actual second point that I've got there that's in the 6 o'clock window, and if I want to know exactly what the value was at 6 o'clock, Flow will not perform an interpolation of that data. So the value will never ever be this interpolated point. The value will always be a stair-step solution. So that first point that we will use inside of my 6 o'clock window will be the point at 55.5, and we will move that forward to be the value at 6 o'clock. So very important, Flow does not interpolate. We use the raw data points as it has been stored inside of my historian. Now, if we draw this graph a little bit different, you'll notice if I draw it as a step line, it makes a little bit more sense. And we will use this little point here as the boundary value. Now, a lot of historians will give this to us. So if I query most of the historian brands out there, or if I query an OPC HDA data source, they will supply you with a value exactly at 6 o'clock. And that will be the boundary value that we will then utilize in a lot of our aggregations. If it's a more transactional type of database, like potentially a SQL database that you are querying and getting results from, you need to remember that you need to supply us with that boundary value. So we need to understand what that boundary value is, else some of the aggregation methods will not work. All right, so let's take our data and let's look at our first aggregation method, which will be the minimum method. Now, this is quite simple. Obviously, it's exactly what we say. It's the minimum value that's been historized or that's in my data source for that hour. But very importantly, that the minimum aggregation will include the boundary value. So that means this value that's outside of the window, the 6 o'clock window, that value will be used as part of the evaluation to determine what the minimum value is. Okay. Now, if we look at the data points here, there's 2 data points in my window here that's got the same kind of value, which is 1.6, which is the minimum. So the result of my minimum aggregation for this data set that we have will be 1.6. So we'll return one value that gets stored in the Flow ODS, and that will be my 1.6 value, because that is the minimum value that we have, including the boundary value. Okay, so that's quite simple. What will we use these minimum values for? Well, you can go and use them for pH levels. So if you want to know what was the minimum pH for the hour, what was my minimum tank level potentially inside of the hour, temperatures, as I explained before, average on a temperature doesn't probably make most sense, but maybe a minimum. If you look at cold supply chain, you want to know what was the minimum of your fridges, etc. So temperatures, quality samples, and pressures, they make very good candidates for minimum aggregations to determine specific KPIs around that. The next aggregation that we're going to look at is just the opposite of minimum, and that's the maximum of the hour. And again, as you could have imagined, we will definitely use the boundary value inside of our maximum retrieval. And in this case, if we look at the values that we've got in my little sample data set, there's definitely that value there at 10 past 6. That's the biggest value that I've got. So that is 3. So that will be returned again as the maximum value for my hour by looking at the sample data set that I've got here. And again, what will you use maximums for? Very similar to minimums. Again, it will be on pHs, tank levels, temperatures, quality samples, and pressure type of related process variables that we will configure our maximum aggregation technique. All right, second one is a range. Now, the range kind of follows on minimum and maximums. The reason I say that is what we will do with the range aggregation, again, including the boundary value, is we will look at what was the maximum value for the hour, and we will go and subtract what the minimum value was. So if you can remember, the max was 3, the minimum was 1.6. We'll subtract the 2 from one another, and then obviously the result of our range will be 1.4. So that is what the range will give us. It will perform that aggregation technique on top of that. And what do we use ranges for is storage levels. Very important to see what was my minimum and maximum range of storage, so I can see if I'm depleting or actually filling it up efficiently, as well as a quality sample. So if I can see, does my quality sample have a very big range? So is it something that I need to control a little bit tighter with my control, as well as temperatures? Is my cold room temperature set point being adhered to, or is there a massive range between my min and my max temperatures? So it can very, very easily point out very bad control that we might have on stuff like temperatures and quality samples, etc. All right, the next aggregation that we're going to look at is a sum. Now, as we see, or as we would expect, what will a sum do? A sum will take all of the data points, excluding the boundary value, because the boundary value for the previous hour would have been used in the sum from the value of 5 to 6 as time buckets. So we're not going to include the sum inside of what the total of these combined is for this hour. And what we'll do with the sum is literally take each and every point and we'll add them together for the hour. We don't see this quite a lot being used in your typical kind of process variables that we store in a historian, like temperatures, pressures, flows. It doesn't really make sense adding temperatures together to give you one massive value. But where we do really see this is in transactional type of data. If you've got a transaction that gets stored in a transactional database every time you offload a specific weight, very important to add all of those weights together for the hour to see how much total weight have you been offloading for an hour. Also makes very sense for transactional, financial transactional data. Production transfers from one tank to another tank. You want to see what was the total transfer for the day. And as I explained, not something that we really use in time series process variable type of historian data, but definitely transactional data sources, we use the sum aggregation. Right, next aggregation method that we've got is what we call the first aggregation. So what that means is please return me the first value for the hour. And in this case, we will return what we call the boundary point. So that is the first point that I've got in this hour will be this value at exactly 6 o'clock. It's the value that we bring forward. Again, we do not interpolate. It is exactly that point. And that is the value that we will return when we have a first aggregation method applied on top of our raw data. Where do we use that? We use that for tank levels mostly, but it's not something that we see a lot being used in normal time series data as well. Now, the opposite of first is probably then last. So the next aggregation method will be the last value for the hour. And again, if we look at our data points here, we've got a data point there just inside of our 7 o'clock window, which is that last data point there right at the end. And that is the data point that we will use to determine what the last value for this hour is. And that will also be the first value for the next hour if we use the first aggregation because we use the boundary value. But in this case, it's the last value for this hour. And that will be the value that we will record exactly at 7 o'clock. If it's outside of that, obviously it will be excluded from the evaluation. And if the data point, so let's say we were very lucky and the historian recorded a value exactly on 7 o'clock, it will not be used in the last retrieval. That will then move over to the next time period. Okay, so if I had a point exactly at 7 o'clock here, we will not record that as the last. This point will still remain the last point that we will retrieve for this hour. And this point will then move over to the next hourly time bucket. So in this case, our last value is 2.2. Where do we use this? Quite useful, again, for tank levels, stock levels. If you want to know what was your stock levels at the end of the day, and also very critical for mass balancing to see what did you end up at the beginning of the day, what did you end up at the end of the day to do your mass balance reporting. Right, then we have a concept of a delta. Now, a delta retrieval will take all the raw points that we have, including the boundary value, and it will go and see what is the difference or the delta between each consecutive point. I'm just going to bring up a little other table here so it will make up the explanation a little easier. So what we will do is we'll say, okay, I've got a data point at the top of the hour, so that will be my boundary value. The next data point that I have is 2.3. What we will do is we will take the 2.3, we will subtract the previous value, and then we end up with the delta. So the delta between these two points is 0.0.7. We'll do this for all of the consecutive points going forward, and we'll see what is the delta between each and every one of the consecutive data points. In the end of the day, we will go and add all of the deltas together to give us the total delta for the hour. So if we do that very quickly and we do the math and we add all of these deltas together, the result of the delta retrieval will be 0.6 in this case. Cool. Where do we use deltas? Again, we use deltas quite a lot in tank levels, stock levels, and it's a very good indication. Are you busy increasing or replenishing your stock? Or are you busy to draw out of your silos quicker than you can replenish it? So is that delta in a negative scenario, or is it in a positive scenario? Then you know that you are actually replenishing your stock inside of your tank levels, inside of your silo levels. So it's a very good indication on the depletion of stock in your production facility. All right, next one that we have is the count retrieval. Now the count retrieval, what it will do is it will go and not include the boundary value. And all that it will do is it will go and count the number of samples that's in this hour. So in this case, I only have 12 points inside of my window between 6 and 7. So the count will, in this scenario, bring back the value 12. Okay. I think count will be probably better served when it's a discrete Boolean type of value. So an on-off signal of a motor, open and close kind of command on a valve, because in that case, I can do things like cycle counts or machine start counts or stroke counts. So it's very used in that type of scenario when I want to look at how many times did a machine start for a day. I can use the count retrieval on that signal or on that pulse to just count me how many times that occurred inside of the day. All right. Second one, or another aggregation method that we have that's quite very powerful is what we call the time in state aggregation. Now what I can do is I can say, you know what, I would like to filter out and only see how long was my process variable in a particular state for the hour. And then Flow will go and look at these different states. It will go and determine what the duration between these different state conditions are, and then return the total duration for me for the hour. So let's look at an example. So if I want to know what was my state where my process variable was 1.6. So I want to know exactly how long was this process variable equal to 1.6 in my data range. Now we've got 2 points that is in that condition. The first point, which is our boundary value, right? So we will include the boundary value for the time and state equation. And we also have another point here at the point number 9 that was equal to 1.6. So what we will do is, obviously we will move the first point forward. So we'll only start counting at 6, not 5:55. We'll move that timestamp forward to 6. And then we'll see how long was it in that duration. So from 6 o'clock to 23 past 3, the total duration that it was in that 1.6. Remember, we're talking about the stair-step condition. So it's actually that little time portion there. So from 6 o'clock until it changes to the next value, that duration there is that what we will record. We'll do exactly the same for the second point. So from 1.6 until it changed to 1.8, in this case, that was a total of 360 seconds. And then what we will do is we will add these together to give us a total time that it was in that state for the hour. Now the result will always be back in milliseconds. So we will return you a value in milliseconds for the time and state value for that particular hour. Cool. And as I said, we definitely use the boundary value in that condition as well. All right. Very useful when we look at time that certain process steps take. So if you want to know how long was my CIP processes for the day, I can use the time and state equation for that. And also very powerful if I want to look at utilization of my pieces of equipment. How long did my piece of equipment run for this hour or this shift or this day? So it's very powerful to determine utilization and process step duration inside of my environment. Variance. So what we can also do is we can look at the variance for our data set. And again, we will use the boundary value for that. And it's very important to understand that when Flow does variance and standard deviation aggregation methods, we will use what we call the statistical population variance or the statistical population standard deviation. So we do not take a sample set of the values in the hour, which is what a standard deviation or variance aggregation method will do. So we will take all of the points in our sample set and including the boundary value to go and to perform our variance. The best way that I got to explain what the difference is between a population variance and a normal variance is, let's say you've got 4 friends. You guys wrote a test and you want to see what the variance of your test result is, or what the variance of your standard deviation of your test results is. But you use all 4 of your test results to do that equation. That is what we call a population variance. We use all of the points that we've got to our disposal. If we have 100 students and we only picked 10 of the points to do a standard deviation, that obviously is we took a sample out of that population and we're only using those 10 points to do our standard deviation. But Flow will use all of it. It will use all the points inside that's available for us to determine our variance result. And again, we can use this for process parameters, recipe parameters, control parameters to see how far we are off from our control. The standard deviation, again, exactly the same. We will use the boundary value in there and do a population standard deviation. Very powerful when we also want to look at recipe parameters, set point versus actual. So if you want to see how far are we off from our Six Sigma control kind of environment, so it's being used to drive that Six Sigma control philosophy to try and have your control band as close as possible to your set point. So very powerful using that standard deviation aggregation method in that. All right, then we get to the counter or the totalizer. This is now, as I explained earlier when we had the concept of adding time as a context to our process variables, if you have that totalizer value that's either been totalized inside of your PLC or by the instrument. So it's a value that increments as the time as it goes on, and then at some point it resets back to 0 and starts its incrementation again. Now, it's very important to understand when that reset happens because that will influence, obviously, how the retrieval method works. So it works almost like a delta. It will take the difference between the points, including the boundary value, and then, obviously, it will detect if there was a rollover. So you'll notice my data points that I've got here, it's always incrementing as the totalizer increments. And then all of a sudden, at 0.9, it resets back to 0, and then the counter starts again. So the values must be incremental when we talk about totalizers. Else we will think, obviously, that a rollover occurred, and we will add whatever the difference is from 0 to the new value as the total for that next hour. So we will detect these rollovers automatically within Flow, and we will then go and add these values together. Now, there's 2 points here that we must discuss, and that is potentially the rollover value might not have been historized at that particular point. So potentially we might not have a value inside of a historian at exactly that rollover condition. In this case, rollovers occur when the value is at 3.5, but the last value that I've got stored in my historian was 3.2. So we're actually missing those little points of values there. So that might occur if we do not exactly log the point before we roll over from our totalizer inside of our historian. But in Flow, we can go and specify a fixed value for the rollover. So if we do miss it, what we will then do is obviously, we won't go from 3.2 back to 0. We will go from 3.2 to, in this case, 3.5, add that little bit, and then only go to 0 to determine what the total is. So we can set that if it is a fixed value that it always uses to roll over. So if we do that, and if we do fix a number of 3.5 as our rollover value, then Flow will compute a value of 3.9 for this rollover amount. And I'll show a little bit of the differences if you do not set it, if you do set it, what the result of those values are when we look at the demo a little bit later. Okay, again, where do we use this? Obviously used a lot in totalized values, might be weightometers, might be flow meters, weight scales, and obviously if we look a little bit more in production lines, bottle counts on filling machines, we use that quite a lot with our totalizer aggregation method to get the totals of these production figures for our particular time frame. All right, the last aggregation method we're going to go into, just explaining before I do a little bit of demo, is what we call our time-weighted average aggregation. Now in Flow, you'll notice that we've got an average aggregation setting, but by default, that average aggregation is always a time-weighted average that we apply to the data. So if we look at our data here, what we will actually do is we will go and determine what the weighted value of each and every point is in the system. Okay, remember we've got our boundary condition. So yes, we will definitely use the boundary condition in our time-weighted average. And the time that it was in this condition until it changes to the next point is 203 seconds. Okay, so we'll use this duration that the value was in, and we'll actually divide that by the total duration of the time bucket. In this case, the total duration of the time bucket is an hour. So the weighted value for the entire hour for this first point is then a result of 0.09. And we'll do this exactly for each and every point to get what the weighted average of each and every point is. And as I explained, we will use the boundary value in this condition again, but the duration will obviously always be from 6 o'clock to the next data point change, not from where that value actually originated from. Okay. All right, so we'll do that equation. So we'll take the duration that it's in this point, we'll divide it by the total duration of the period. In our case, it's an hour. So we'll divide that by 3,600 seconds, and that will then give us the weighted value, and then we'll add all the weighted values together to give you the total time weighted average for the hour. Right, where we use this? If I've got a raw flow transmitter that produces cubes of water per hour, and I apply the time weighted average on top of that raw data point, the result will actually be the total water in cubes for the hour. So it will actually do a little bit of an integral of that to get the area underneath the graph, if we think about it from a mathematical perspective, and it will give me the total area underneath the graph. So in essence, it is the total that's been produced by that flow transmitter. It is the total of tons that's been going over my weight scale if I've got the raw tons per hour signal coming in from my field, and not a totalized value. So I can actually use the time-weighted average aggregation method, apply it on a raw transmitter value, and it will give me the total for the hour. And it will be the exact same value as what I had for a counter retrieval if I had a totalizer. Okay, cool. I hope that made a little bit of sense on what we do for a time-weighted average. Just for an interest sake, if your data in your historian is stored in, we always kind of promote delta storage, so only store when the data changes. But if it changes and it's periodic, so every 10 seconds, you store a data point in your historian, a time-weighted average and a normal statistical average will give you the exact same value. Okay, cool. All right, so that's me explaining all the different aggregation methods. There's too few of them that I'm gonna demo, the custom one that we can actually go and configure ourselves. So let's go into Flow and see how we actually configure this from tags, potentially from our historian data sources. So I'm going to move across here to my Flow config. And you'll notice that I've configured a whole bunch of aggregation methods already. So I've got a min, a max, an average, a first, and in each of them I've got my hourly KPIs or my hourly measures configured that I'm now applying these aggregation methods upon. I've got two data sources that I'm currently connecting to. I've got a historian, a time series data source. I also have a transactional type of data source, in this case a SQL database where I've got all my transactional data in. So if I open up this measure, just an example, my minimum measure here, if I open that up in the configurator and I look at my retrieval settings, you'll notice that in my retrieval setting is where I can go and specify all my different retrieval methods. In this case, I'm getting it from a SQL database. So I'm querying a normal transactional database and I'm applying my minimum data set on top of it. And in this case, the data set that I've got prepared is exactly the same values as what I've been talking through in the slides. Just for interest's sake, if I open up my query here, you'll notice that I do return my boundary value. So I know exactly what my boundary value is from my SQL data source. Obviously, if it's from a historian or an OPCH DA source, it will return it exactly for me on that hour what the boundary value is. And then to determine the aggregation method, it's a very simple kind of drag and drop environment. Okay. Select your aggregation. Flow will then go back in time, look at all the historical data that I've got, so I can backfill on the historical data, and it will perform the aggregation method here, and in this case, store the result inside of my little ODS for that hour. And that's the only value that we store, is that value for the hour. Cool, I'm going to deploy this out again, and let's build one from scratch. So I'm going to just create a new metric here for me. It's my Tech Thursday session that we've got. And this time I'm going to go into my actual historian. Now in my historian, I've got a utility section where I've got a boiler. And in this boiler, I've got a flow transmitter. And the output of that flow transmitter is obviously the amount of steam that this boiler is supplying to my plant that's been used in the process. And what I would like to know is, what is the total of steam for the hour? So it's very simple. We browse the namespace or the tags that's been historized inside of the historian. So it's very simple for you to go and search for those tags and to create a KPI or metric inside of Flow to start cleaning the data and applying the different aggregation methods on top of it. It's simply a drag and drop operation. So I take the flow transmitter that's been historized. I can drag it across here to my little metric, and that will automatically create an hourly aggregated measure for me inside my flow system. And in this case, I can give it a nice normalized name. So I can say this is my steam production for the hour. Perfect. Open that up. It is the raw steam that I get from this transmitter. So if I look at the data for this steam transmitter, just give it a little bit more room here. So this is a flow transmitter. It's not a totalizer. This is the raw value as it's been historized inside of my historian. We don't duplicate those raw values. We just have an I on top of it so you can see what aggregation method you need to apply to your raw data. So in this case, I know it's the raw flow transmitter. So I would like to obviously in my retrieval do an average or that time weighted average retrieval to get the total tons for the hour. Now you'll notice there's a few other things that we can do here. And you'll notice that my flow transmitters actually give me kilograms per second. If I integrate over this, and I want to know what is the total potential tons for the hour, I need to scale these values, because the unit of measure for this is not kilograms per hour, it's kilograms per second. So if I wanted to apply a time-weighted average to this, I need to scale the seconds to hours. If I want to convert it from kilograms per tons, I need to scale the kilograms per tons. Now, scaling kilograms to tons, divide by 1,000 seconds to hours, multiply by 3600. So the scaling factor in this case is going to be 3.6. So now I'm converting kilograms per second to tons per hour. So my unit of measure is now going to change to tons, because I'm already in an hourly time bucket. So if I look at this value, it will actually be the tons of steam produced for the hour. So I can go and deploy that out, and that will give me my aggregation here. Now, I can even clean this data up even further. So potentially I would like to know what is the total steam produced if the boiler is actually active. So I can go and add what we call a filter tag. And in this example, I don't have a Boolean that tells me that the boiler is active or not, but I've got the temperature, right? So only when the temperature is above a certain range, then I know I'm actually producing steam. And I only want to go and determine what the flow of steam is in that condition. So I can take this temperature tag, I can add it to the filter condition here, and then I can say, you know what, only when temperature is greater than 80 degrees, please start and performing the time-weighted average of the total. So I can go and build out quite neat filtering capability here, just to clean that data even more before I present it to my end user. Cool. Now, you'll notice that I only have the capability to add one filter tag. So currently, I can only add one filter tag to the stock standard aggregation methods that we've got. But what if you want to do quite a complex filter of the data before we apply the aggregation method upon it? So let's look at an example. This is great. It tells me what is my total steam that's been produced for the hour. But what I would like to know is I would like to create a KPI that tells me when my boiler is in very specific process parameters. Now you'll notice that I've got a pressure transmitter on my boiler, and I also have a temperature transmitter. So I would like to know when the pressure is in a certain range, as well as when the temperature is in a certain range, tell me how long the boiler is in that optimal design state. So how well am I utilizing my boiler in that exact state that it's been designed for to be operated in? But I want to use multiple variables. So obviously I can't just use one filter tag. In that case, I need to use a custom expression. So what I'm going to do is I'm going to create a new measure here. In this case, this will be my design rate time and state measure. So I want to know exactly what is the time that it is in this particular design state. So I'm going to open this up. And underneath the retrieval section here, obviously I can't use of the predefined ones, but I can go and create what we call a custom expression. All right, so I'm going to go and add the custom expression editor here. It's going to ask you to go and configure an expression. And there's this little ellipse button here that will open up the custom expression editor. So if I click on that, it gives you this kind of namespace and definition editor where I can go and build these custom expressions in. A little bit of a trick, if you double click on this, it will do it in full screen. You've got a nice big area or real estate to actually build your custom expression. Now what I have is I've got the entire namespace available for me. So again, all the tags that's inside of my historian. And I can actually now add more than one tag to use in my expressions. So I can use the flow tag, I can use the pressure tag, I can also use the temperature tag. So I've got 3 tags that I can now utilize inside of my custom expression. Then you've got this big blank hole here to actually write your expression. Right, but we do have some examples for you. So you'll notice if you hover across the example tab here, it does give you the capability to add examples for custom measure expressions, trigger expressions, and event expressions. I'll probably cover these two in further text sessions. The one that I'm going to cover today is just our normal measure. And you'll notice that we've got examples how to do a row-based sum as well as a row-based average aggregation there. So I click on that, it will, in the average one as an example, it will just give you a little bit of an example code of how to create your custom expression and how to get the values for each and every row that's been returned for each and every one of my tags that I've added into the expression. All right. In this case, I'm doing a very simple statistical average. So I'm adding all the values together, dividing them by 3, and taking the average of that. Right, we don't want to do that. What we want to do is we want to say, when my process variables are in very particular states, look at what the time of those are, the time and state of those. Now, the nice thing is that I can actually use the flow aggregation methods inside of this expression. So I can get to the time and state aggregation method. I can use the standard deviation aggregation method that's been supplied by Flow. Now, I've done this a little bit earlier, so I'm gonna just copy the script quickly here. So I've got a little script prepared, and I'm just going to copy quickly here. And I'm just going to paste that in here. There we go. And now we can see what the values, what we are doing. So we're saying, if my flow transmitter is greater than 4.1, I also want to know when my pressure is greater than 1.4 bar. And I would also like to know when my temperature is greater than 98 degrees. If it matches all of those 3 parameters, then return a 1, else return 0. So what am I doing? I'm actually taking my analog process variables and I'm converting it to a discrete tag, a 1 and a 0. If it conforms to all 3 of these conditions, return 1. If it doesn't conform, return 0. So I've got a discrete representation of my process parameter limits that I've got here. And what I then can do is I can then tell Flow, you know what? I've got a whole bunch of 1s and 0s. Please utilize the time and state aggregation that Flow provides and tell me what was the time in state when these values that I've just created is equal to 1. All right, so I'm building up a list, a row list of all of these conditions, and I'm just telling Flow, please go and determine what the time and state is when it is into 1. So that will then now tell me what is the time and state that I'm in this optimal design rating or this optimal design frequency. Cool. I can then check that I haven't got any spelling or issues in my equation, so I can click there on the validation button there. It will validate my code, and I'm ready now to deploy this custom expression. So I'm gonna just minimize it again here, hit the OK button, and I'm gonna now tell the Flow engine to run this custom expression. Again, it's gonna backfill, it's gonna query the historical data, it's gonna perform this custom expression aggregation method on top of the raw data, and when it's done, it's gonna give me a result. Now, it doesn't look like I'm in this design rating quite a lot. So let's just pop it out here. Let's give it a little bit more time on the time frame perspective. And I haven't backfilled far enough. Sorry about that. So I'm just going to backfill this a little bit long from the 1st of September. Run through this again. And let's see if I can actually catch this boiler when it's in this design rating. Let's see. Here we go. Cool. I've got some time. So I've got some time and state that it's actually been in this design rating. It's not a lot of the time. It's not all of the time. So obviously I can improve on this time and state rating. Cool. Let's quickly put this on a dashboard so we can just see what it would look like from a reporting perspective. So I've got all my KPIs here for all of the different aggregation methods. I'm just going to add this custom one that I've got here onto there as well. So I'm just going to add a chart here, an hourly chart very quickly. and I'm going to add this design rating in there on the axes. And I'm going to say, you know what, just show it for me for the past 2 days. And I would like to see it as a column chart. Perfect. Right, so let's see the results of all my different aggregation methods. So I'm going to go into the web server now, where we host all our reports and dashboards. So this is the web server, HTML5, the rendered reports and dashboards. I'm going to go to my little dashboard that I've got here, just created. There you can see when my boiler was in my specific design rating. And let's just change this back to when I actually had values in my transactional database. And there we go. So there's my min value. If you guys can still remember, the minimum was 1.6, maximum was 3, the last, the first, the time and state when it was 1.6, the counter value, the standard deviation, and then very importantly, you'll see that I've got 3 widgets here that shows me my counter values. Okay, first counter value is a counter value with no rollover value specified. So we're missing that point from 3.2 to 3.5. So you'll notice that why there's a difference between the counter value here and the counter value with the rollover. So if I go back in the config tool and I go here to my counter, you'll notice that this counter here has got no rollover configured versus my counter with rollover has the value of 3.5 configured. That's why these 2 values are different. Well, and I also have a counter value that's faulty, which is completely different out of the ballpark. It's a very big number. And the reason why it's a big number is because the values are not incremental. So there's false rollovers that occurred inside of this data point. If I look at that values actually inside of my data point in my database, and I go do a select on those, you'll notice that I've got values, but it's not incrementing. So there's 1, then goes 1.7, and then it drops to 1.6. So if values are not incrementing up until the rollover point, Flow would have thought that a rollover occurred at that point. And it will wrongly add 1.6 to my result. Again, if I look a little bit down, there's another one that caused an issue. So again, Flow will add another 0.1 to that because it sees that as a rollover because the value is less than the previous data point that I've got. And that's why you see that big value change inside of my faulty counter value. It's something we get quite a lot on tech support, counter values that's quite massive. And 9 times out of 10, it's because that the totalizer value inside of my historian is not incrementing. There is a gap inside of that. We can either go and fix that at source in the actual process condition, or we can add a deadband to say, you know what, let my totalizer at least change with 0.3 or 0.4 before we go and have that aggregation method applied. Cool. I think I'm running a little bit out of time. It's almost the top of the new hour. So I'm just going to go back here into my presentation here. And let's see if there was any questions that we've got. Just opening up the chats here. Okay, is there any questions? You guys can either use the chat or the Q&A function. If you do have questions, I know we're running a little bit out of time here. If you do have questions, feel free to email us, support@flow-software.com, and we can go and answer those questions. This recording will be recorded, obviously. We will send out the link of this recording after the session. And then, as I mentioned, please be on the lookout for our following tech session. It will happen on the 22nd of October. And what I'm going to talk about there is, how do I get data from a web API? So in this example, I had data from a plant historian, also had data from a SQL data source. But what I'm going to do in the next tech session is talk a little bit about how can I actually interrogate a web server API to get data, that kind of data inside of Flow, and use that inside of my calculations and aggregations. Perfect. Thank you so much, guys, for attending our session here. I hope it was insightful. If you've got any comments or any other topics that you want us to cover, please give us a shout as well, and we will work that into our additional tech sessions that we have. Thank you very much.